Okay, hello. Today is a tutoring session, okay, for the part of ordinary differential equation and introduction to partial differential equation. Okay, in the previous ed clip, okay, we have go through, the lecture page by page as you see on the screen, okay. Uh, and along the way, you can see that we have given you some of the question, like I give you an example here, okay. On page 6, okay, this is a given, okay, the second order system, the classical second law of Newton's, okay. Suppose you are given a boundary condition, okay. What would be the general formulation for the displacement function, okay, given to initial value condition problem, okay. And along the way, we also ask you many questions, okay, after this, okay. For example, okay, after this we also have this homework question on page 17, okay. Okay, we want you to derive a general form. So, okay, this is the first one we already talked about. The second one is this one when we consider the full second order mechanical system, okay, with both the spring, the mass, and and damper, okay, and with the general governing equation. And also we want you to derive general forms, okay, when given force function is in the polynomial order R and or in the summation of many sinusoidal with different frequencies, okay. And and along the way we also when we talk about the higher order system, okay, we also ask you about this. Remember on page 28, okay, derive the formula, okay, and also uh, for the current function for this third order system, okay. You might recall this is a third order system, okay. And okay, with the high order we also leave you with some very special fifth or sixth order, okay, or system, okay, with a more simplification for the input function, okay. Just want you to have an idea how complicated it is, that when the order of the system keep increasing, okay, in terms of DOE, okay, no, ODE, okay. And for partial differential equation, we also asked you to review and also apply many knowledge, okay, like we want you to derive what we call the on page 66 the third dimensional, okay, heat equation, okay. As again, this is a second order, okay. And for the three-dimensional, okay, we also have this for Laplace equation, two-dimensional, and two-dimensional heat equation, okay. And toward the end, okay, we also ask you to do some homework about deriving the general forms of three-dimensional Laplace equation, okay. And almost at the end for the way also we also leave you with the final question about the wave equation here, okay, the general form. Okay, and today we're gonna try to give you some hint or some give you an exam, some extended analysis from these lectures note, okay, to when you apply to those homework assignment, okay. And you can see that on the screen that we have a small folder in my Google Drive, okay, that called homework here, okay. If you double click, get it in, okay, you get into another page by page, or of about almost 40 pages of reviewing. I prepared this note that in with my expectation they're going to help you to solve those question that I asked on the lecture note. Okay, so we're gonna go through this page by page. Okay, in not so much. We're not gonna spend more explained time, just like what we did on the lecture note. Okay, so we're gonna start now with page number 1. Okay, for homework, page number 1 down here. Okay, this is you might recall our very first question. Okay, when you have electrical circuit of a series system with the resistance, inductance, and capacitor. Okay, and suppose that the input voltage function, okay, is in the form of polynomial order R. A sub 0 plus a sub 1 times t plus a sub 2 times t squared plus up to a sub r times t to the r. Okay, and with this classical governing equation based on the Kirchhoff voltage law, okay, it is obvious that you can write down this second order differential equation. Okay, so okay, I already changed the integral form of the voltage across capacitor. Okay, and as a 1 over d. Okay, you might remember the d operand, and this is a resulting uh, second order ordinary differential equation. And with this question we already did based on the lecture note. Okay, we did what we call the initial condition. Okay, by giving you the I at time 0 and the first order of I at time 0. But in this question we ask you if you given you the boundary condition, for example, that t is between the length the range of start from 0 and then end up at capital T period. Okay, we giving you the initial current, okay, at time 0 and the ending current at time double t, capital T. As you know that when t is greater than t, okay, the IT is equal to 0. Okay, just like when you have a short, you open circuit here, okay, at time 0, and then you short circuit at time at capital T. Certainly with this ordinary differential equation, you can know that based on the general solution for the ordinary differential equation, IT can be written as a complementary solution, as a subscript here, I sub CT plus I sub PTP coming from particular solution. Okay, as you know that since the type of function of current, okay, since it's appear on the left hand side, it's a response you're looking for, rely on the type of input function. Okay, and in this case the input function is in the first order of the voltage function. Okay, and you know that since the input of a voltage function is the polynomial order R, therefore the right hand side function here, the first order of ET, is in the polynomial of order R minus 1. Okay, it's obvious because you find the first order derivative. Therefore with this type of right hand side, okay, it reflects what we call the general form for I sub PT, particular solution. You can see that I sub PT is in the general form of polynomial, but the order just reduced by 1, only from R to R minus 1, since the right hand side is not really the direct function of ET, but it's a first order. Okay, and therefore, okay, it's obvious in this case that for complementary solution is the same. Okay, it's the same to what we did on the, if you go back to the lecture note. Okay, this one. Okay, this general solution here. Okay, here this is a resulting equation we explained before. Okay, you can go back. Okay, and this is what the complementary solution. The complementary solution is the same. We have three cases. Okay, three cases, and in each case, okay, this is the resulting general form for the complementary solution. But for the particular solution, okay, this one is for a particular solution that we already explained that it's going to be polynomial order r minus 1. And certainly you can substitute I sub pt to both sides, okay, and e sub t on left hand side or I sub pt, and put e as a function of t, okay, to the right hand side, okay, and then you did what we call the coefficient comparison, okay. This is we already explained before, okay, so I'm gonna move forward here, okay, and then you know that I's complementary solution consists of three cases. This one already explained that, okay. In case that you have both of the auxiliary equation imply you have both the real roots, okay, and thirdly now you have in case one, if s sub 1 and s sub 2 is both the real value, okay, which means that the condition that r divided by 2 times L all together square must be greater than 1 over L times C, okay, which imply that the value in the square root is always the positive value. Thus resulting both s sub 1 and s sub 2 is a real value, okay. Therefore you just the difference is that you once you know in this general form, okay, you don't have to worry much about the I and this is I took the results immediately from what we study in the lecture note, okay, and so but the difference is that how do you find c sub 1 and c sub 2, okay, in the complementary solution, okay. But now you are having the boundary condition I at time 0 and I at time double t, okay. You just substitute t equal to 0 and t equal to double t, okay, you get two solutions, and result, and suppose both of these solution is can be 0 or non-zero, whatever you can define, okay, resulting that you have two equation, and each with the linear equation, okay, two linear equation. Since you know the s of 1 and s of 2, in reality once you know the RLC and you know the interval time of the capital T, okay, the right hand side you know the initial condition and the at time 0 and the boundary condition at time double t, okay, not double t, the capital T, okay. So you end up having to solve the just a direct linear equation with two variables that you can apply the Cramer's rule, and this is a general form of C sub 1 C sub 2. In the case in the case that both root for the auxiliary equation is the real value, okay. And then you can go on doing some similar way analysis with case 2, that since you have both these both roots are real, okay, and all and equal, okay, and you have equal root, okay, here, and this is a general form, okay, according to the ODE methodology, and this time you can derive and get the general form of C sub 1 first, okay. This one is not resulting in the equation just like case 1. You can solve C sub 1 immediately from I at time 0, and once you know C sub 1 you put it in the I at time equal to double capital T, okay, and then you get the C sub 2 here. And in the third case here, also similar to second case, is that when you have a complex conjugate, okay, I mean that you have j equal to square root minus 1, okay, you have complex number, and then have a property what we call the complex conjugate. The real part is the same, okay, and imaginary part are also the same, except that the sign, okay, one is a plus, the other is a minus. Real part plus imaginary plus j times the imaginary part, and the other one is a real part minus j times the imaginary part, and that resulting, this is the resulting general form, okay. And when you apply this general form at t equal to 0 and t equal to capital T, okay, you get this condition, and then you can find C sub 1 and C sub 2 in general form. Yes, this is quite pretty straightforward, okay, that that help you. Actually, this one I almost did this do it all for you. Okay, just a basic idea so you can see, and now you can extend that knowledge to this system. Okay, it's one of the homework from the lecture note that I gave you in the first couple of clips. Okay, on my lecture script also. Okay, so now you can see that this is a general governing law. Okay, equation. Okay, for the second order full mechanical system. Okay, so the characteristic or auxiliary equation is in this form. Okay, then you find the root, okay, in general for the quadratic equation. And now you have case 1, case 2, case 3. Okay, and this is pretty similar to what we did with the second order RLC circuit. You can see that I give you the example. One is a mechanical, this is a mechanical problem. The other one is a classical electrical problem. Okay, that you should be familiar from the basic physics course. Okay, so again, okay, when you have case 1, 2, 3, also the case 1 is both two roots are real value. Okay, second one both a real value but have the repeated root. Okay, the same value. Okay, the third one is a complex conjugate. Okay, that resulting in the general formula. Okay, for the x complementary solution for the displacement function. Okay, and in this one, okay, when you have the what we call the polynomial order R, we can apply pretty similar but you can see that this one is different from the example of the RFC, because the right hand side the relationship between the type of function of the displacement and force are directly related. Okay, which means that the type of function force function applied to this system, okay, we reflect the type of pattern or function for the displacement directly, because comparing to the RLC, that the right hand side because the first order of the input function. Okay, therefore you can see that once the force function is in polynomial order R, therefore the particular solution for displacement function is also in polynomial order R. And the rest is history. You just derive for the general form for the first order, second order, for the particular solution of displacement and put it back. Oh, sorry. This is what we're gonna do. Okay. We're gonna substitute this. Okay. Okay. Back to this equation for the left hand side, and then you substitute the force function to the right hand side. Okay, and we perform what we call the comparing coefficient on both sides. Okay, this one, m times second order plus c times plus k, and then force function here. Okay, ft here. Okay, this is the left hand side expanded here. Okay, yeah, and then rearrange the term. Just rearrange the term so that you get you can compare the form. But either like this one is comparing to ft is it must be equal to 0. This is a constant term, and the coefficient that multiply t can be compared to a sub 1 here for the ft. Okay, and so on until the a sub r and order r for the right hand side of f function t. Okay, can be compared to here. And this is, and you can now get the what we call the recurrent equation. Okay, that you can do something like back substitution with the order polynomial order r. You get this relationship. You get, once you know a sub r, which is the input force function, you can find b sub r here. Okay, and k, you know, there is a spring constant. Okay, and also, okay, r is a polynomial, c is a damper constant. Okay, and k, and so on. You can see that I already derived this back substitution form from b sub r up to b sub 0. Okay, by that's resulting using a similar technique that what we did with RLC circuit here. Okay, and next, okay, is you combine, okay, complementary solution and particular solution all together. Okay, you get the general form for the displacement function. Okay, and I'm not gonna continue to do this for you in this case because it's a similar way that what we did. I just put it here. It's similar to the previous problem, the ILC problem. Okay, and this I get the rest to analysis, okay, remain for you to continue and finish the problem. Okay, and you use the previous example to as a prototype, okay, to perform further analysis. Okay, for the second problem is that when force function is in the form of what we call the summation of m terms, okay, for each term, okay, consists of what we call the sinusoidal function, the amplitude time cos function and cos function of some what we call the angular velocity, okay, the omega j, okay, time t, okay, and with a similar omega also, okay, this is omega j also, but this is the psi function, and b sub j is the amplitude, okay. So this is in general, if you might recall from basic physics or basic electrical engineering class, we call this or in mechanical engineering we study this, we call this a vibration. Okay, it's a vibration form. Okay, and it's a combination, okay, of several type of periodic what do we call the periodic sinusoidal, okay, signal, okay, combining together. Okay, this one is a different the resulting of x complementary solution is still the same because complementary solution does not rely on what kind of force function is. Okay, yes, therefore in general form x of ct is the same, but the difference will be x of pt since ft is different. Therefore, ft or as what we did from the previous example, that you can that you know that f sub t uh, dictate what we call the pattern of x sub pt. Since here is the summation of some sinusoidal function, that resulting x sub pt is also the summation and also the m term of sinusoidal function also. But at the same angular, okay, velocity, okay, omega j, okay, and both of these are sine omega j and cos omega. But the difference is the amplitude, okay. The input function have the a sub j and b sub j as the amplitude for cos and sine respectively, and but for the response of displacement of particular solution, we set up as an f sub j and g sub j. Therefore, once you already using f sub t to dictate the type of x sub pt, the rest is we're doing something similar to what we did when you assume that f sub f function of t is a polynomial order r. We are doing the comparing coefficient technique, so we need to find a general form for the first order and second order. Okay, this one is that f sub j is a constant value, but you find the derivative. This one is a function of t, cos of omega jt. Okay, derivative of cos is minus sine, and then you need to find derivative of what inside the cos also, which is omega jt. And since this is a linear function, you get omega j here as a derivative of omega j times t. And also g sub j, okay, constant, but when you find derivative of sine, you get cos, and then you get omega j from the derivative of what inside the sine function. Okay, and this is also expanding to the second order. Okay, this is the second order of response function, displacement function. Okay, you get this, and once you get this, you put all this back to the what we did similarly, that to this original governing equation, and then you get what you call the comparing the coefficient. The left hand side become here. I already arranged the term for you. Okay, there will be some term multiplied by cos omega jt and the term that multiplied by sine omega jt. Since the right hand side is in this form, okay, it arranged with amplitude times cos omega jt and another amplitude times sine omega jt. Therefore, we rearrange once you substitute this to the left hand side, okay, and then you rearrange the term, okay, so that you get what is the term that multiplied by cos omega j_t, and combining all the term that multiplied by sin omega j_t, and then this resulting to this when you compare, okay, here, therefore it's not easy, it's not very easy to see that how do I get this metric equation for the two variable simultaneous linear equation, okay, this one, because this one have to be equal to a sub j, and this term that multiply on the left hand side sin omega j_t must be equal to b sub j. And then again you have a equation with two variable, therefore you can find the general form, okay, find the determinants, no, yeah, this is the determinants and the inverse function for this metric form, okay, multiplied by this vector of the right hand side, okay. But this one is only for a specific j. You have to make sure that you can say that j is running from 1 2 3 up to m, so it's an independent, okay, two simultaneous linear equation with the total amount of m type, okay. And so this one is if I end up you get x sub pt in general form now, so because you can find f sub j and g sub j in terms of a sub j and b sub j, okay, based on this relationship. And then the next step is that you, if you know, in this case we're going back to the classical initial value problem, that suppose that at time c equal to 0 you have two conditions of the zero order and the first order, okay. And also we have to analyze this in what we call in three cases also, okay. This is the first case when s of 1 and s of 2 is two real root, okay, real value, okay. Suppose that x at time 0 and x at the first order at time 0 can be, normally we assume it's equal to 0, but it can be any value, okay, constant value. So therefore again we bring back to use the general formula of solving simultaneous equation with two variables to get this general form to find the constant of c sub 1, c sub 2 for case 1. And then in a similar way from the previous example in case 2 and case 3, but just you have to apply to the right input function the x sub pt, the particular solution here. Okay, I'm not gonna explain this as much. It's a very direct and straightforward that you need to analyze on all possible cases for the constant of c sub 1, c sub 2, c sub 1, c sub 2. So this is quite complete for the problem of what we call the second order system. Okay, but again for this one, this is another example that you need to apply what we call the mesh analysis resulting from the KVL, the Kirchhoff voltage law, okay, to solve for what we call the loop current, okay, of I sub 1 as a function of t, I sub 2 as a function of t, and I sub 3 as a function of t. Okay, and once you apply this is from basic electrical engineering or basic physics 2, okay, you get this differential equation, okay. It looks like a first order, okay, but multivariate, okay, with three response at the same time from I sub 1, I sub 2, and I sub t with the input function of et, okay. But in this case, okay, you can get the general form of I sub 1, I sub 2, I sub 3 as a function of t by applying the Cramer's rule, okay, to get the corresponding ordinary differential equation here. When delta 1, okay, as you know that delta is the determinant of this the left hand side matrix, okay, here, okay, and delta 1 is by replacing the right hand side vector in the first column of the left hand side matrix, you'll find the remaining determinants, okay. Delta 2 is replacing this right hand side vector to the second column and found the remaining determinants, okay, and I sub 3 also for the third column here for the left hand side matrix, okay. And in this case, okay, we're gonna go through a little bit because since it's only the uh, 3 by 3 matrix, okay, so you can, as you might remember, this is a high school knowledge of finding determinants or the formula to find determinants of matrix psi 3 by 3. Okay, and this resulting for you to get this third order, okay, differential equation as a delta here. Okay, we have d operand as d by dt. Okay, this is delta, and then for this case we find delta 1 here. Delta 1 is replacing the first column here, okay, by the left hand side function, okay, here, okay, and then you get this determinants of this matrix, okay, this is delta 1, so this is 1. And to simplify, because it's already in a function of the system parameter there, which is consists of, if you look at back at the R, the 3 resistance and 5 number of inductance, okay. So delta is in general form, okay, for 8 parameter, as you might say, then 3 resistance number and the 5 what we call the 5 value of the inductance, okay. And also delta 1 also is in a general form, okay, with d as d by dt. So we simplify this, okay, this is one we call b pi sub 0, b pi sub 1, b pi sub 2, okay. Okay, this is a pi sub 0, a pi sub 1, a pi sub 2, and a pi sub 3. So this resulting this general form, okay, for the ordinary differential equation. This is in the third order form for the response function of the current function time t in the first current loop function, okay, in the network, okay. And you can do similar analysis for I sub 2 and I sub 3t. Okay, this one just only give you an example, give you a hint for the current function for the first loop only. Okay, so this is a corresponding differential equation, and you can continue to do for the second order and for the third order. Okay, and you can see that it's quite obvious. I'm not gonna if you unless you do it, you will find yourself that the left hand side function is the same, because if you look at the general form here, you normally, if you move delta to the left hand side, okay, it's the same delta value, which is the determinant here. Therefore the left hand side function here, okay, the left hand side function here, the multiplied by here, therefore the left hand side function here, okay, is always the same. The a pi sub 3, a pi sub 2, a pi sub 1, a pi sub 0 is the same for both first I sub 1 or I sub 2 and I sub 3 as a function of times, okay. But the difference will be the left hand side. The left hand side is belong to this delta 1, delta 2, and delta 3. Okay, so this delta value is lead you to, you can see that like in this one delta 1 you have, you have e the input function of e at time t here. So the difference will be the right hand side. Therefore, in terms of analysis, the complementary solution of all I sub 1 and I sub 2 and I sub 3 is the same. Okay, it's the same. You just do perform once, okay, analysis for I sub 1. You can use it for I sub 2 and I sub 3 for general form. But the difference will be I sub pt, the particular solution, because the right hand side change, okay, not the same for I sub 1 and I sub 2 and I sub 3. Okay, we not you can see that a lot more alternative and a lot more possible solution here. Since now the complementary solution, I already told you that is the same. Okay, this one is I give you the superscript of 1, which means that the loop current for this one for the first loop in the circuit here. Okay, so this one, certainly the first one is that for all of them have the distinct real root, okay, real value, not non-equal. But if you have a pair that equal, that not does, and also the other one that's distinct root, this is a general form. The pair that equal, you need to use the repeated root form, okay, that you can use the superposition technique that apply to each case for the second order and extend it to the third order here. Then this one is for the distinct root. And the third case is that they have all three roots are equal, we call S sub 0. And this one you can extend from the C sub 2t to the third root that equal, okay? You have C sub 3 and then time t square, okay? And this thing you can keep extending if you have four same where four same for the four root in the case of fourth order and fifth order and so on. Okay, this is you can see that we can extend the analysis from the second order to the third order here. And but in the last one, okay, if you consist of a pair consists of complex conjugate, the other one must be the real root. It cannot be complex because complex number you have your conjugate, you need to have two root, okay? And also you can expect that you might wonder that is it possible if you have three complex root, okay? The solution is no. If you have one root remaining, that root is automatically must be the real root, okay? Cannot be three complex number, okay? But it's interesting if you want to prove it, okay? Okay, but this is when we just apply the knowledge immediately. So, and again, j is equal to square root minus 1. Okay, and in this problem, instead of we based on the homework that I assign you, we give you an voltage function in the very easy form. It's not the summation, just like the second order homework that you have a m terms of sinusoidal function. This one just a direct sinusoidal function, only one frequency omega, okay, angular velocity of omega, okay, and with a single frequency interested, okay. And again, ET, okay, dictate what your IPT gonna look like, okay. And you might remember thinking about that. Okay, in this case, okay, you can see that the right hand side, okay, is not just rely on ET themselves. They have consist of both first order, zero order, first order, or second order. But why do I assume that once ET is in the sinusoidal function of sine and cos, the first the I super in the first loop of the circuit I1, okay, for sub PT here, it's also the sinusoidal with different amplitude of capital F and capital G. Why don't I you remember that when the left hand side the right hand side have different order, okay? For example, if they don't have the zero order, if they don't have the zero order, okay, if you have a differential polynomial order R, okay, therefore the IT have to be polynomial order R minus 1, because this one they conserve the first order here, okay. But since the right hand side consists of the zero order, therefore IT automatically, okay, is dictated by the type of ET, okay. Therefore, and also if you might remember that it doesn't matter even if you don't have the zero order in terms of sinusoidal function, because when you find the derivative of sinusoidal function, you're going to end up have the alternate, no matter how high the order going to be. Going to be sine to cos, cos back to sine, and so on. So that's why it's all have the same format here. And now you have a third order system. You remember that here? You just put the find the general form of particular solution, okay, for the third zero order, first order, second order, and third order, and put all of this, okay. And also you need to find the first order and second order for the ET function also, because you need to use it to substitute for the right hand side for this corresponding ordinary differential equation. And the next step is a little bit more complicated, because you are gonna do the what we call the it took some more time to rearrange this term to do the what we call the coefficient comparison. Okay, when you're comparing these coefficients, okay, again you can find the general form, okay, to find the amplitude of f and g, okay, here when for a given amplitude of a and b, okay, with the given of b sub 0, b sub 1, b sub 2, and b, and you know that this b can be found when you once you know a pi 0, a pi 2, and a pi 3. okay, because no, you know a pi sub j and b pi sub j immediately because of this substitution that you assume here when you're trying to simplify the general form from solving this Cramer's rule, okay, corresponding ordinary differential equation, okay. And then once you make the comparison, you get both, okay, here, okay. Now you know that you can solve for f and g, and certainly when you're looking for the second the I2 I sub 2 which is the second loop here, okay, for this one, or I sub 3 here, okay, you know that this f and g formula going to be different, okay, case and case by case, okay, it's going to be different, okay, uh, not depend on what we call the complementary solution, but this one is different case by case from once the for each case of the loop current, okay, for all three of them, okay. So it's you need to derive the other for the new one for f and g, the corresponding simultaneous equation here, okay, for case of I sub 2 and I sub 3, okay. But the result that you can keep using the same for I sub 1, I sub 2, I sub 3 is here. Is what we call the four cases of the general form for complementary solution. Okay, I'm gonna go by this in a pretty quick way. Okay, that for case 1, okay, you can see here, you end up having a 3 by 3 corresponding simultaneous linear equation, and then you can apply the Cramer rules, okay, to get the general form to solve for c sub 1, c sub 2, c sub 3, okay. This one just the direct substitution, okay, and we didn't use the boundary condition, we used the initial condition, okay. But now the initial condition need to you need three of them, okay. You need zero order, first order, and second order at time zero, okay. That for the first case, for the three distinct root s sub 1, s sub 2, s sub 3, you end up need to solve this equation to get c sub 1, c sub 2, c sub 3. And then this one for I sub 2 and I sub 3, okay, this one I give you that, okay, you need to find delta 2 and delta 3 and put it in this form, and then both of it say, both became two another third order differential equation similar to I sub 1t, and then you can do similar way to analyze it. And also the complementary solution, in this case I already did one case, okay, I already for case 1, but how many cases you need to analyze, okay, you go back to this form that this one you have three more cases, okay. This I already did the first case, you have second case, third case, and fourth case, okay. So plenty more work to finish this problem, and you can see that the amount of analysis just start to increase a lot once you change the order of the ordinary differential equation keep increasing here. Okay, and we move on to the next example. This is the third order. No, this one become the what we call, since each mechanical system represent the second order, when you have three system connected. From our lecture clips, okay, you can already see that with the two mass you get the fourth order. So when you add one more, you end up having this type of what we call the mechanical. It's a similar analysis that what we did with in case of the KVL from the previous example. But this one we just do, you just did the what we call the free body diagram, okay, for each mass, okay, m sub 1, m sub 2, and m sub 3. You end up having these three corresponding governing law, or second law of Newton, okay, to get this equation. And again, similar to what we done from the previous example, but just the order of the corresponding ODE is just higher than, because this one resulting to the three response function, and then you end up having a second three second order equation with multiple response, okay, three of them. But if you want to just write down just only one response equation, okay, you need to apply the Cramer's rule, okay. You get different for x of 1 and x of 2, x of 3 in terms of time t. The similar analysis than what we did from the previous example. You need to find delta 1, delta 2, delta 3, and then you need to find delta 0 and rearrange the term. With the rearrangement of the term, delta 0 is a determinant here, okay, determinant of this left hand side matrix, okay, and then you end up having this d to the 6, which is resulting what we call the, okay, just simplify the form, okay, a pi sub 6, a pi sub 4, a pi sub 2, and a pi sub 0 in terms of, the system parameter consists of 3 mass, okay, and 3 value of k of the spring constant, okay. And this is the in the easy ways to find delta 1. Delta 1 is that when you substitute this, okay, the right hand side vector function to the first column of the left hand side matrix and find the determinants here. This is I skip a lot of step, okay, but this one is the determinants, okay, according to the Cramer's rule. And this one is with the simplification, okay, of a pi sub 6, a pi sub 4, a pi sub 2, and a pi sub 0 with b pi sub 0, you end up having what we call the the higher order ordinary differential equation. In this case, the order extends to 6, okay. And in this problem, I try to simplify for you that suppose that f of t is not the polynomial function, it's just a constant, f is a constant. Okay, but since this is a 6th order, therefore you need 6 initial condition, okay, which is x 0 order, first order, second order, third order, fourth order, fifth order, okay. Okay, and so you need up to this order 5th, okay, as the initial condition. And therefore for in this case, then ft is a constant force, therefore you know that once you find the derivative, it's always 0, so therefore you can apply directly that in a steady state condition, okay, for particular solution for displacement of mass number 1 is equal to b pi sub 0 divided by a pi sub 0 times this constant f value, okay. But certainly if you want to use the similar example that we did from the previous example, if ft is a polynomial function order r, or is a summation of the sinusoidal function, okay, you need to perform to find x of xi particular x of one particular solution, you need to perform what we call the coefficient comparison also, okay, to get the general formula that related from the force function in general form to the general form for the displacement of the mass number 1, okay. In this one, okay, so in this case, since force is a constant function, you end up only consider complementary solution, okay. This one I'm going to do just case 1, which is a distinct root, okay, which means that this time you have 6 order, therefore there exists of the uh, root, the real root, okay, 6 unequal value, okay. So this is the general form, and that resulting with the 6 initial conditions start from order 0 to order 5th, okay. You end up having the 5 by 5 equation here and comparing with, okay. And suppose that I give you that this condition, in this case we simplify that all the 5 condition initial condition is equal to 0. But if you want to leave it just like what we did from the previous example, you're not going to get 0 here, okay. You in the first one you're going to get x pi 0, okay, minus this one you get x pi of 0, x double pi, x triple pi, x at 4th order, okay, at time 0, and x at the 5th order at time 0 on the right hand side, okay. But this one is a little more, more nasty if you want to find the general form of c sub 1 to c sub 6, okay, because you need to find the inverse of this matrix, okay. Actually this matrix is another well-known form, okay. We call this a Vandermonde matrix, okay. And the Vandermonde matrix is there's some way you can find the general form of inverse also, but that quite pretty advanced in terms of mathematics. But since I already said, if you are interested, you need to go to the Google form and search term is what we call the Vandermonde matrix, okay, and then you find you might try the inverse for the Vandermonde matrix. Okay, once you know the inverse here, you use that inverse then multiply to the right hand side vector here, you get the general form from C sub 1 to C sub 6. Okay, therefore you can see that, and the case, this is only one case, okay, to get this. Okay, and uh, and you know that this minus is, where is this minus coming from? This one is coming from because the right hand side here, okay, have only zero order here. Okay, okay, therefore once you go for the uh, just the first one, okay, that you have at time 0, okay, that you end up having this constant, but the first order here, okay, the remaining force function here, okay, becomes 0. Okay, that's why the resulting is 0 here. Okay, okay, but if this is become a non-zero, okay, this initial condition, if become non-zero, you can move this, okay, and put it in as the initial condition here. Okay, and on the right hand side. Okay, and next step, okay, we're gonna consider that, what do you think that how many possible cases for complementary solution of x of 1t? Okay, this is just one case, you have 6 distinct roots. Okay, what do you think that how many possible cases? You can see from the previous example, okay, when you from second order system you have 3 possible cases. For third order system you have 4 possible cases. But when we are skip now from the fifth order, we now to the sixth order. Okay, I'm gonna tell you is the combination increased a lot. Okay, and then in each case you get just the first problem, it took a lot of time for you to enumerate all possible. Okay, just think about it, and then if you, this is for only x of 1 complementary solution, you want to find in general form for displacement of mass number 2 and displacement function of mass number 3. And also the third question is even more serious, that once you get ft here, okay, as a polynomial order R, what is the general form for x of 1, x of 2, x of 3 in terms of 3? This is also the open question that you can continue to do based on what you learn from this tutoring clip. And okay, the fourth question is that you can use previous illustration. Okay, consider this alternate current circuit, that when the input function is m terms, okay, the summation of n term of sinusoidal function here. Okay, but this one you have, you have RLC. Okay, that, and you can expect that this also leading to the what you call the sixth order. Okay, if you want to derive the general independent ordinary differential equation for I sub 1 and I sub 2 and I sub 3, each of them is going to be the sixth order. Okay, just like what you found, what you just found in the 3 mass problem here. Okay, and also you can see that just tremendous amount of work. Okay, especially you need to be able to answer this first question first. Okay, because the combination can be up to, I think, 20 something or almost 30. Okay, I'll give you a hint, less than 30 cases, but more than 20 cases. Okay, if you enumerate all possible, oh, it's going to take a lot of time. And then remember that this one I give you the lead example for only one cases for complementary solution and a very simple input force function. Okay, but if you consider this is the third question, and you just enumerate all possible cases for the first question, it's gonna take a lot of time for you to write down the general form. Okay. Okay, that's the thing that you should be interested to expand. Okay, and do it. Okay, Let me tell you the condition that I'm looking for, okay, for the final evaluation of this course is that so far you can see that along the lecture clip, including today's, okay, tutoring clip, okay, I give you some solution of the previous example question that asked you. But again, each of these questions you can expand it up to this point, okay? And I want you to use this knowledge, okay, trying to finish all of this if possible. But it's a lot, I know that, okay? But just try to do as much as you can, okay? And you need, each one of you need to have just a book, okay, just a notebook, okay? And you need to write down this solution by your handwriting, okay? Mark my words, okay? Your handwriting, not typing in computer or anything. Okay, let's go back to the basic high school days. Okay, I want you to write down, okay, by your own handwriting. For each of you, you need to have your own notebook. Okay. Just say that this is a homework notebook. Okay, you write down all to answer this open question and also the uh, extended question that I asked you here, okay? And do it as much as you can because it's, it's gonna take a lot of time and to answer all of this question, and you cannot do it within 3 hours for the of the you cannot do it in 3 hours for on the in-class exam. That's why I give you this as a challenge, okay? Whoever can do the most, okay, for what I said so far, okay, would be the one that get the most pointed, okay? So the harder you can, the more opportunity you can gain the point for your final exam. Okay, so that wraps up this part for the ordinary differential equation. Okay, this one we're gonna extend it, so not a little bit here for a couple of pages. That we go back to the question that open question that I asked you when we start lecturing you about what we call the okay in this lecture note. Okay, let's go back to the lecture note. Okay, just beware that from the lecture note here, okay, so far, okay, you can see that we answer this almost every question here, okay, but not quite finished, okay, so you can go back and try to finish it up some of this question, okay, from the homework, and also for this one, okay, we haven't, especially we didn't link it with the general form for the cubic equation that to find the root of cubic equation that I mentioned before. We still haven't bring that condition, that in what condition that the root will be have the distinct root, okay, or a pair of root equal the distinct from the other, and so on. Okay, so we didn't link the data for Wikipedia. This just like what we did on the second order problem. Okay, so this also then an open area for you to investigate and add it up for on your homework book. Okay, and also this problem, okay, we talk about the combination for the input function that both they have polynomial order R and also the m terms of sinusoidal function here. For so far we analyze for you only each case separately, but suppose that the input function is a combination of these two, how it's going to look like. Yeah, so this one is uh, not covered at all yet, okay. And also for higher order question, okay, uh, this one still haven't finished yet, okay, that for the third order one, okay, for to analyze for all cases and for when you extend ET, okay, to become the polynomial order R for the general formula for IT, okay, that's from the first example for the higher order case here, okay, you might go back and recall, and this one is a fourth order case, okay, when you have, I also asked you the fourth order cases have some extensive analysis, and also toward the end there, this lead you to this example that I start giving you solution for, but not finish it all, okay, just give you a hint for the start, but these two problems can waiting for you to finish it up and adding it up with and go back to the what we call the homework page here. Okay, that wraps up with the remaining open question here. Okay, to finish it all. So plenty of work. Okay, and you can have time until the last day of your final exam schedule. Okay. Okay, so let's just say that I order you the exam from today. Okay, this is the first part that based on the first 8 clips that I already uh, put it on YouTube channel, my YouTube channel. Okay, so and a lot of work that can be done here. Okay, and in the next step, we're gonna go to the question that I asked you about partial differential equation. When we study partial differential equation, you might remember that. The basic idea is that we study what we call the second order partial differential equation, that we found application in 3 classical physics problems. The first one is a classical one we call the heat equation, you might remember. And we giving you the full analysis that lead you to the general solution form, which is in the form of Fourier series. Okay, and under both Dirichlet condition, boundary condition, and Newman boundary condition. Okay, and we also extended the result on from start from the one-dimensional heat equation to two-dimensional heat equation, and after finishing the two-dimensional heat equation, okay, we start asking you, okay, this is the very first question, derive a general solution for the three-dimensional heat equation, and considering both Dirichlet and Newman boundary condition. And again, okay, you might remember I forgot to put this second order term, okay, in corresponding to y and c. Okay, make sure that you put 2, okay, as a second order term for these two term in the for the three-dimensional heat equation. Okay, that extended, okay, the boundary condition in a similar fashion. Okay, and that's the first question that I asked you after giving you a very long period of understanding the derivation of the general solution for both one-dimensional and two-dimensional heat equation. Okay, so therefore in each case, okay, in this case we go back to the homework page subfolder. Okay, and for the tutoring session, start from page no, I have to start from page 22 here. Okay, we talking about, okay, this one is a little bit, you need to expand it a little bit. Okay, this is a three-dimensional heat equation. Okay, it's not a little bit unclear, but based my mistake on taking the picture. Okay, and you have what we call the boundary condition. No, the boundary of finite bound of x domain, y domain, and c domain, as starting from 0 to alpha for domain x, and 0 to alpha y for domain y, and 0 to alpha c, okay, for domain c. And this one is a general three-dimensional heat equation by expanding. Okay, this is a correct equation, and alpha square is a positive value here, and t, okay, have to start from greater than or equal to 0, and you have a boundary condition, okay, for each domain x that start at time okay, at the boundary condition, okay, for start at boundary of x and boundary of y and boundary of c, okay, for any specific time t is all equal to 0, except that at time 0 at time 0 for any domain of x, y, t with this finite value is equal to function of you see, it's equal to function of x, y, c here. So this is an expansion, and this is what you call the Dirichlet boundary condition. Okay, and therefore I'm gonna believe that you've been following the clips talking about an analysis of both one-dimensional and two-dimensional heat equation before, that we can apply what we call the uh, what we call the Fourier method, or the separable domain function here. Since now you have four domain, now you have domain of the space of x, y, z, and domain of time t. Okay, this is a u function, which means that is a heat, okay, that's spread, okay, over coordinate of x, y, z at time t. Okay, or you might say that heat represents as a temperature. Okay, but capital T, use capital T. Okay, and you can know that this general function can be written in a product form for each domain function of capital X in as a function of X, capital Y as a function of Y, capital C as a function of C, and capital T as a function of T. Okay, and this one we extend a similar analysis here. Okay, if you put this substitution of this product form of this separable function to the original heat equation, okay, you end up having this relationship. Okay, since the left hand side is the first order corresponding to t, so that the xyz as a separable function, it become a constant. Okay, and you find the first derivative for only t. For the second order, okay, on the right hand side, the alpha square is a common multiplication. You put it out here from the inside for each term, that the second order corresponding to each domain. So the first domain is the substitution of u, and except that they have a second order for the domain x, and second order derivative of domain x. The second term is second order derivative of domain y, or y function, and the second order derivative of the z function. Okay, and pretty similar to what we did with the second order, we can extend to the third order. With this one, if you divide it on both sides by the original formulated u, okay, as a product of x, y, z, t, okay, and rearrange the term, you end up having this relationship. Okay, and then you can separate and put it in to get this four corresponding equation. Okay, if you don't know that how this equation 1 2 3 4 come from, go back to the analysis and the clip that I taught you about two-dimensional heat equation here. Okay, so this one you get here. Okay, all of this, and then the next step is that you just go on to, okay, make a substitution of p, q, and r. Okay, and then put this substitution. Okay, this one is a little bit clearer. Okay, and you end up having this simplification form of first order of ODE of t function. Okay, and then from here, okay, you're gonna get ODE function for this four equation. Okay, the first start with the t function here. Okay, and then you get this, okay, for the x, y, z. Okay, and since the right hand side is 0, you need only to find the complementary solution here. And this one is just expanding the analysis in case of you have three dimension. You can go back and observe from the first dimensional, second dimensional, first dimensional only x function. In two dimensional you get x and y, but for three dimensional you get x, y, and z. Okay, it's in this form, just an extension similar to what we did for the first dimensional or second dimensional. Okay, so, and finally, okay, the t function is a little bit different, but it's an extended form. Okay, you remember that from two-dimensional you only have p and q. Okay, now you add r for the c dimension, and you have instead of you have lambda m sub n. Okay, for two dimension you can add one more index of s. Okay, lambda m n and s. Okay, and this one is another one, and then this resulting to the general form of u, x, y, z, t. Okay, and next you need to find the general form for the constant value of b star sub m n s. Okay, and you can expect, as you might see in that the general form for the first order is in the series, okay, summation to infinities, and as you know that we call the one-dimensional Fourier series. For two-dimensional, it becomes double Fourier series. And for three-dimensional, as you can guess, is in this form that with that boundary condition that given you here, okay, ux, y, z at t equal to 0, this resulting what we call the triple Fourier series. Okay, it's in the triple form of Fourier series. And this one is a mistake a little bit. It should not be 6. You remember that for two-dimensional you get 4 divided by L sub x times L sub y. But this one for the three-dimension should be 8 because it can be 2 times 2 times 2 because or 2 to the 3. This should be the 8 value, not 6. Okay, and this is the integral for the triple Fourier series. Okay. And also you know that with Dirichlet condition you end up having the coefficient in terms of the sine function, okay, but for the Newman function you just change the sine to the cos function in a similar fashion, okay, that you can see that this is a this is a mistake, okay, it should not be 6, it should be 8, okay, and this coefficient can be found, okay, under using the extend analysis that what we did from one-dimensional, two-dimensional, and can be extended to the three-dimensional. Okay, so that wraps up this question that we asked you, okay, during the lecture clips of the two-dimensional heat equation, okay, and you can see that if you go back to another question, okay, that from the lecture note, okay, we from the very last clip, okay, over here, okay, you go to the last page of the clips, okay, we did ask you about what about the wave equation, okay, what about, oh, I'm very sorry, okay, because what I did for you here, okay, from the homework, we just talked. Oh yeah, correct. That's the heat equation. Okay, we from the example that I illustrated to you is a heat equation, but this one very similar analysis, except that the left hand side becomes the second order instead of first order. This one you know already know this is a wave equation, and also we add a little bit that the boundary condition is a little bit complicated, okay, actually not complicated. If you study from the last clip, okay, before this clip, you should be able to expand this result for the three-dimensional wave equation, just like what we show you on the part of okay, from this homework tutoring form, okay. So I think that with this solution here from the last page here that I told you, remember that this is not the 6, if we change this to 8 coming from 2 times 2 times 2, okay, and you can extend it for Newman condition, and also you can use similar analysis here to analyze the last question from the clip from the previous clip, okay. I'm talking about the derivation of general solution in terms of triple Fourier series also. Let's just but just in the different form a little bit, because the sine and cos function probably not going to look the same, because this is a heat equation which is slightly different from the wave equation, okay. So the remaining part that you need to know is that when you were assigned to solve what we call the 2 or 3 dimensional Laplace equation, and also this one is not in the lecture yet, but I asked you a couple of questions in the lecture clips that related to this topic that we need to talk about, and I give you some hint of the idea. In this case, we call the two-dimensional Laplace equation with inhomogeneous boundary condition. What is the inhomogeneous boundary condition? Visually going to be different from the classic, what we call the homogeneous boundary condition. Okay, let's go back to the lecture clips. Okay, a little bit about the Laplace when we analyze the Laplace equation. Okay, you might remember that. Okay, we start analyze Laplace equation in here. Okay, on page 67. Okay, that resulting the extension from the heat equation that when you don't have the heat flow change over time, therefore resulting to the classical what we call the Laplace equation. And certainly when you did give you an example, okay, case by case, okay, and then I give you after this solution with example, I ask you this homework equation that because you can see that in this case all the boundary condition have some constant where it's a non-zero, and it have no general function. It will be different from the example, okay, that I analyze for you, that in this case you get this general solution, but c sub 1, c sub 2, c sub 3, c sub 4 change due to the boundary condition. The example that I gave you is that they have a constant value, okay, for a boundary non-zero boundary condition on one side. The remaining for two dimension, so you have four side of boundary condition. Okay, only one side is have a non-zero constant, but the other three sides is all zero. Okay, but when I ask you in the homework, okay, for this two-dimensional Laplace equation, okay, or even the heat equation here, okay, you can see that we 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 separate this, okay, we have non-zero, okay, in this one, and this one is also non-zero. Okay, so the technique that I'm gonna tell you, give you, okay, in the tutoring next, okay, can be applied to solve these two problems. Okay, which in these two problems we have a boundary condition that in the form we call the inhomogeneous boundary condition. So inhomogeneous is not homogeneous. Okay, so what about homogeneous condition? Homogeneous condition is have to be, okay, just like for Laplace equation, okay, two-dimensional Laplace equation, sorry, it have to be in okay, in like this one, you have only one non-zero, the other one, the three is zero. Okay, and for the heat equation, okay, if you go back to the heat equation, the boundary condition is all here. Okay, the heat equation here, okay, this one, okay, the Dirichlet boundary condition is all zero. Only at time zero you have a specific f of x1. So this is what we call the Dirichlet homogeneous boundary condition, and also Newman condition also. You have the zero boundary condition here for all area of for the boundary point of all domain x and y, but for at the starting point of domain t, okay, is equal to some specific function. So this one leading you to the get you the general solution in term of Fourier series. Okay, okay, that's the example that we illustrate for you. But for the homework question, okay, if you I ask you here, okay, in this one, this two, it become what we call the inhomogeneous, okay, in both case of Laplace and also the heat equation. You can see the heat equation here, except u of x, y, t0, this one is homogeneous, but you can see that for the boundary of x, okay, from 0 to 10 here is 0, but for the boundary of y become the non-zero. So this one become the inhomogeneous in case of heat equation. But my last hint for you, okay, to give you the idea to solve this problem, okay, I give you an example, okay, the way that we analyze second order partial differential equation when facing what we call the inhomogeneous boundary condition. Okay, but I'm not doing for the heat equation. I give you this example for only one. This one we call the for two-dimensional Laplace equation as an example. That because it's you can see that the whole idea is like this. Okay, this one you can see that it can be any general function. Doesn't have to be a constant also, but it become a general function. It doesn't have to be three psi only zero. Can be any function. Okay, at for each boundary. In this case of Laplace equation, you don't have boundary at t equal to 0. But for all boundary of x, okay, from the lower limit to and at the upper limit, and for the lower limit of y and upper limit of y, can be equal to some specific function according to the remaining domain. Okay, we call this one called inhomogeneous Dirichlet boundary condition. And also the technique that we analyze so far, we what we call the homogeneous boundary condition. Okay, and to be able to use the technique, the Fourier method or variable separation or technique, we must make sure that okay we can decompose this inhomogeneous equation as a superposition of these four conditions, and these four conditions, each of them is the homogeneous case. Okay, so the whole idea is that we must decompose this to the four cases, the additive. Okay, we call additive is mean that if we in each of these cases, okay, it become you can apply directly to the previous example that we already apply, okay, from the lecture clip, except that the boundary condition change, okay, side by side. Okay, so this boundary inhomogeneous boundary condition is equivalent to this four homogeneous equation in analyze in a similar fashion of when we use the superposition technique. Superposition is mean that for each response of u, okay, you can apply each of this case, okay, and find general solution for each of u, and then you can add it up at the end, okay, to get the general form to answer the whole question of this. Okay, so in this one, okay, I'll give you a whole idea briefly in a pretty quick way. Is that you decompose this to this six condition, and if you extend this to the three-dimensional, you're gonna end up having a six uh, additive homogeneous boundary condition. Okay, because in the six three-dimension you have six sides, okay, of the rectangular box. Okay, if you might try to imagine, okay, just like in this case for the two-dimension. So this is what we did so far. Okay, the first analysis is a case number one. Okay, I'm not we apply this technique again. Okay, case one and three. Okay, we can choose, and why we choose minus value of lambda square, because it lead you to a non-trivial solution. Okay, you might know that if we choose vice versa, okay, so in the opposite side of this chosen value, okay, condition, you end up getting a familiar what we call the trivial solution. And once you know this, okay, you just apply this is a become homogeneous, the classic one, ux0 is equal to f1 of x. You we already did this, okay, in the example of two-dimensional Laplace equation. Okay, you end up get the general form here. Okay, you get the tan-ish. Okay, here we already did this. Okay, so I'm not going to go to this again. So this one you get, okay, x of y, y of y, you get this one, general form. Okay, this is just almost copy from the previous analysis. Okay, but and also the b star sub n here, okay, is in the Fourier series form. Okay, one-dimensional Fourier series form. Okay, but this one is only the case here. Okay, this is the case here of f1 sub x, again the ux0 here. So you need to apply those kind of technique with this boundary condition, the remaining three boundary condition. Okay, so this is the first case. Okay, when you have f1 of x. Okay, and then you have second case. Okay, this one you have g2 of y, L sub x y. Okay, in this case you choose plus value to lead you to a non-trivial solution. Okay, and again you can go to this step by step. Okay, you can uh, very similar results that what but just exchange the function due to the different boundary size, okay, of the non-zero boundary size that we used to analyze previously, okay, from the clip of two-dimensional Laplace equation. And this one could go directly straight, okay, step by step. Okay, you can do see that this application this one you get this solution, and now you get this general form, okay, of Fourier series coefficient of c star sub n. This is for uxy for this second uh, oh, it's a little slow, sorry. I go forward. Oh, this one, okay, we analyze this is the second case, g2 sub y, g2 of y function. This one, okay, this is the second case. Okay, the second case. Okay, this one get the general solution here too, with the c star n is in, or they can be derived by using this coefficients finding according to the Fourier series. Okay, in a similar way, the third case we choose here, you get here, okay, with the general form. Okay, and the last case here. Okay, and once you get the results here, okay, this is the last case, and general form is over here, u function is here. Okay, and with h star n, okay, is in, can be derived from this form of Fourier series method. Okay, and then toward the end you end up the solution of uxy for each of this separate analysis of homogeneous boundary condition. You add four of them. Okay, this one's the first case, this one second case, third case, and fourth. When b star sub n, c star sub n, g star sub n, and s star sub n can be derived, okay, according to the formula previously shown. So this one is you can see there is a superposition technique. Okay, so you separate each of these boundary condition to become the homogeneous boundary condition, and then apply what we learned to analyze solution for each case, and then you combine, you can use that, sum it up, okay, the result for each case, sum it up to get the general form of u of xy. Okay, so this is the technique that we can analyze and help you to be able to solve the remaining question from the partial differential equation lectures. Okay, which is we can go okay, we have we still have the last question here, open question. If we extend that analysis to the three-dimensional, okay, but this one is in the general form of inhomogeneous function, okay, for boundary condition. Okay, I want you to once you already learn here from the two-dimensional, can you extend it for the three-dimensional Laplace equation, which certainly gonna relate it to double Fourier series formula. So, okay, I think that if you watch the clips for partial differential equation with 4 clips, okay, again and again, you can see that this tutorial clips, okay, is just as extensive of a similar analysis that you have done. Okay, but just extend to a higher dimension or a little bit more complicated of boundary condition. Okay, and that should wraps up, okay, here that uh, the very last question here that I asked you, okay, from the last script, from this one. Okay, that you should be able to do this and extend this analysis for two-dimensional Laplace to the original two-dimensional heat equation. Think about it, and I think that with that example you can lead you to be able to perform, to finish these two homework. And also for the three-dimensional, the open question should help you to, when you apply it back to solve with this three-dimensional boundary condition, because this is in just a given linear function for the boundary condition instead of general f of x or xy, f of yc or f of xc. So, but if you go back to the extensive question from the last page of this tutoring, the homework subdrive here, okay, if you be able to do this problem, okay, to get the general form here, you can apply it directly to solve the problem. You can apply it to solve the problem here directly. Okay, so that should wraps it up. Okay, this tutorial session that okay, you can go back and rewatch, okay, the lecture clips, okay, that consist of the explanation of the 83 pages of the lecture note in summary here. And also I add you the tutorial of all the question and homework that hopefully can help you extend this knowledge to do the remaining question on homework that asks both open question and open homework remaining part from all lecture clips that we cover so far. Okay, that should wraps it up, the first part of this lecture note. Okay, we still have the final part, okay, that's going to concern the extensive of what we call the Fourier series and Fourier transform. Okay, see you all in the next clip.